So we now go to the Fourier transform is a cap and inverse Fourier transform also we defined, and this cap is defined from L2 of Z to capital L2 of minus pi pi, defined by for Z belongs to L2 of Z. We have Z cap of theta is equal to summation n belongs to Z of n e raised to I n theta, and this Z cap will be in this L2 of minus pi pi. So theta is used here, and the series is this series converges by lemmas 4.7 and 4.17, and 1 minute. This inverse Fourier transform is from L2 inverse cap is from to L2 of Z, and for f belongs to capital L2 of minus pi, we define f inverse of n by this f inverse belongs to L2 of Z, so of n is given here. The inner product between f and e raised to I n theta, that is defined as 1 by 2 pi integral minus pi to pi f of theta e raised to minus I n theta d theta. The map cap defined earlier is we have to show that it is one to one and on to with the inverse cap defined earlier. For Z belongs to L2 of Z, we have Z of n is same as Z cap inverse of n, which is equal to 1 by 2 pi this term, and we have this Parseval's relation, and this is this inner product between Z and W we will get is an inner product between Z cap and W cap, and 1 minute. This Plancherel's formula, norm Z square is equal to norm Z cap square. Z cap and Z have same norm, that is we have to prove. And suppose Z belongs to L2 of Z, and by the same exercise that we have earlier taken, and we have this now inner product between Z cap and e raised to I n theta is equal to what is Z cap is defined. How is Z cap is defined? Z cap is defined as as Z cap is equal to summation n belongs to Z of n e raised to I n theta. So here 1 minute. So Z cap can be written as summation m belongs to Z of m e raised to I m theta, comma e raised to I n theta. This we have in this exercise, we have seen that the answer is this coefficient at this index, that is Z of n. So we have inner product Z cap e raised to I n theta is Z of n. So this Z cap inverse. What is Z cap inverse is defined? Z cap inverse is defined, this inverse is defined by inner product Z cap e raised to I n theta. So this this is Z cap inverse sorry, Z cap inverse of n is equal to inner product between Z cap and e raised to I n theta, which we have got as Z of n. It's true for all n, so we can write that Z cap inverse is equal to Z, that is or equation 4.36. Yes, and we have proved the first one. Z of n is equal to Z cap inverse of n, that is defined as 1 by 2 pi integral minus pi to pi Z cap of theta. Here it is defined e raised to minus I n theta d theta. Okay, this inequality, this equality is proved now, and we have this we have also shown that this cap is 1 minute, because if we have this cap, if Z1 cap is equal to Z2 cap, then taking inverse, Z1 cap inverse is equal to Z2 cap inverse, that is equal to Z cap inverse is Z, so we get in this implies Z1 is equal to Z2. So the images are same, then the inputs are same, that is 1 1, that is cap is 1 1, and this f belongs to L2 of minus pi pi. Then corollary 4 point, this 4.244 shows that this can be seen like that, uh, f inverse cap F inverse cap is defined as summation n belongs to z. This is equal to summation n belongs to z f inverse of n e raised to I n theta is equal to the summation n belongs to z. F inverse of n is defined as inner product f comma e raised to I n theta e raised to I n theta. This is equal to f by corollary 4.244. In 4.244 we can see that this f can be written as summation n belongs to z inner product f e raised to I n theta into e raised to I n theta. So we have got f inverse cap is equal to f, that is f inverse cap is in f inverse cap is equal to f, that is this cap is on to, because for every f belongs to the image space or codomain, we can find in the codomain we can find an pre-image f inverse belongs to the domain such that f inverse cap is equal to f. That is the definition of onto. So this cap is on to, and we have this f inverse cap is equal to f, and uh, z cap inverse is equal to z. So we can say that the inverse of cap is this inverse defined earlier. So these equations are, we have proved that. And this 4.243 corollary, when we apply this to f is equal to z cap and g is equal to w cap, and we get what is 4.243 corollary. We have inner product z cap w cap is equal to, defined there, summation n belongs to z inner product z cap comma e raised to I n theta into w cap e raised to I n theta conjugate. We have defined it in the corollary 4.2 for third one, third equality. We have this z cap w cap inner product between z cap w cap is equal to this one. And this can be this can be written as this z cap and w cap can be written in the form of this. And we get now, 1 minute, we get now this as a summation n belongs to z. This z cap can be represented by summation over m z of m e raised to I m theta comma e raised to I n theta, inner product closed. And this w cap can be written as summation m belongs to z, this w of m e raised to I m theta comma e raised to I n theta, inner product closed, and this is conjugate. And we know from the exercise 4.2.52 we have this summation n belongs to z. What is this summation inner product? We have inner product between two items, and first one is summation, second one is single item. Then the answer is z of, here it is m, here it is n, so z of n into, here also w of m, here w n here, so w of n conjugate. This is the equation for inner product between z and w. So we got inner product between z cap and w cap is same as inner product between z and w. That is, we have to prove. 1 minute. Yes, so here it is an inner product between z and w is same as z cap and w cap. Now, last one we have to prove is the norm z square is same as z cap square. For this, letting z is equal to w in 4.37. 4.37 we put z or w, z in place of w. We get inner product z is equal to norm z square is equal to z is equal to summation z of n conjugate, that is summation z of n the whole square is equal to 1 by 2 pi integral minus pi to pi z cap of theta into z cap of theta conjugate, that is z cap of theta whole square is equal to this inner product z cap, this is equal to norm z cap whole square. So we have proved this Planger's formula. Norm z square is equal to summation mode z of n the whole square, here it is, and this norm z square, and this is also here, and this also here. So we have proved this result, and now coming to the next item, we have this relation 4.3. In relation 4.3, if zw belongs to L2 of z, we have seen that summation n belongs to z, mod z of m minus n w of n will be less than or equal to individual modes norms, that is z of m minus n square raised to half w of n square raised to half, that is norm z into norm w, that is summation mod this one is will be less than or equal to, by relation 4.3 we have used here, and here we have replaced this m minus n by k. So this n belongs to z can be replaced by k belongs to z mod z of k, because the sum is infinite, and we will have all the terms by using this index change. And now definition 4.32, for zw belongs to L2 of z, for m belongs to z, define convolution between two items. We have earlier defined for L2 of z, and now we extend this result for L2 of z. Z star w of m is equal to summation n belongs to z, z of m minus n w of n, the same as earlier we have seen that. And this mod z star w of m, for each m we have will be less than or equal to this one, and summation mod z of m minus n w of n, which will be less than or equal to norm z norm w by this relation. So this this can be proved, uh, this is the yes, this is the formula for z star w. Z star w is modulus of summation z of m minus n into w of n. This is mod. We have to prove that less than or equal to summation mod z of m minus n into w of n. In the finite case, this inequality becomes summation minus n to n z of m minus n w of m, sorry, n. Uh, this this is finite case, and if we take full modulus, it will be less than or equal to summation modulus of z of m minus n into w of n by triangle inequality for finite terms. If this is a sequence and this is a sequence, if for every n, if this sequence has satisfies this inequality, then its limit also satisfies the inequality. Left hand side's n tends to infinity limit is this one, and the right hand side's n tends to infinity limit is this one. So we have this mod of z star w of m, that is this one, is will be less than or equal to the limit of this one. Limit of this one is n belongs to z, or infinite sum. We have this one. This inequality can be seen from here. Earlier we have proved this one. So we will use this item in the following lemmas for the proof, in the proof of the following lemmas. Z star, so remember this, z star w of m is equal to summation mod z star w of m will be less than or equal to summation mod z of m minus n w of n. So what is the interpretation from this less than or equal to inequality? 4.40 earlier we have proved, for zw belongs to L2 of z star w will be bounded for each m, it will be bounded by norm z and norm w. Since z and w belongs to this L2 of z, its a norm will be finite. So this is a finite number, this is a finite number, multiplication finite number, totally it will be a finite number. So this quantity will be bounded for each m. So for m is equal to m belongs to z, we will get a sequence. So, and in this uh, it is not necessary that the z star w belongs to L2 of z. We have defined z star w for zw belong to L2 of z, but here we have uh, noted this summation, but it is not necessary that the summation belongs to L2 of z. It is in the solution manual. The answer is here in the exercise 4.4.62, and it is in the solution manual. For z star w becomes an element of L2 of z, so we will make uh, another statement regarding this. For this, this z can be represented by z of n belongs to z with a sequence of complex numbers, and z is summable. Earlier we have seen what is square summable, now it is summable if the series summation n belongs to z mod z of n will be finite. Earlier square summable, there will be square here, so in this case L1 of z belongs to sequence of complex numbers such that each component belongs to the complex number for all n, and z is summable. Summable means this summation will be finite. Okay, this z belongs to L1 of z define. We define the norm of it. Norm z1 is equal to summation n belongs to z mod z of n as analogous to the earlier part. And this 4.4.2, you can easily prove that L1 of z is a vector space, but it is not an inner product space. This norm 1 is a norm 1 defined here. It is called L1 norm, and uh, this norm is defined in exercise 1.6.5, and L1 of z is a proper subspace of L2 of z. That is in exercise 4.4.2. It is in the solution manual. We have this answer for this uh, exercise. So refer solution manual. That is L1 of z is a proper subspace of L2 of z. That is, there exists at least one element of L2 of z which is not in L1 of z. That is proper subspace. So this in the following cases we will denote the norm in L2 of z, 2 norm, by this norm, this notation, and by in L1 norm we will notate it by norm 1. So norm 1, we have L1 norm, and simply norm means L2 norm. So suppose Z belongs to L2 of Z and W belongs to L1 of Z, then Z star W belongs to L1, L2 of Z. This Z star, the condition for Z star W belongs to L2 of Z is that one of the element will be in L2 of Z and the next one is in, second one is in L1 of Z. And we will prove that the norm Z star W will be less than or equal to norm W1 into norm Z2. Now, for any m belongs to z, summation n belongs to z, z of m minus n into w of n, here n is running, will be less than or equal to summation n belongs to z mod z of m minus n into mod w of n, as we have seen earlier. uh, here here we have seen that uh, this mode means this one will be less than or equal to summation mode. So here we apply this result. This here we have is a modulus of z of m minus n into modulus of w of n. Modulus of w of n can be written as mod w of n raised to half into mod w of n raised to half. Half plus half becomes 1 here. So now by the inequality we have earlier proved, they will be less than or equal to summation n belongs to z of m minus n by inequality 4.3. You refer here z of m minus n സ്ക്വയർ, അതായത് ഇവിടെ എഴുതിയിരിക്കുന്ന ടേംസിന്റെ സ്ക്വയർ, ഇവിടെ എഴുതിയിരിക്കുന്ന ടേംസിന്റെ സ്ക്വയർ എന്ന് പറയുമ്പോൾ ഇവിടെ ഒരു സ്ക്വയർ വരും, ഇവിടെ സ്ക്വയർ ചെയ്യുമ്പോൾ റൈസ് ടു 1/2 റൈസ് ടു 2 എന്ന് പറയുമ്പോൾ 1 ആയിട്ട് മാറും. ദാറ്റ് ഈസ് 1 ഹിയർ, ആൻഡ് വി ഹാവ് ദിസ് നോം 1/2 ഹിയർ, ആൻഡ് ദിസ് സെയിം തിങ് അപ്ലൈസ് ടു ദിസ് w of n mod w of n summation w of n ഹോൾ സ്ക്വയർ the whole raised to 1/2. സ്ക്വയർ എടുക്കുമ്പോൾ 1/2 പോയിട്ട് 1 ആയിട്ട് മാറും. 1/2. It is equal to, this is defined, we have defined what it is a norm w1 raised to half, that is written here, and this summation is written here. Therefore this z star w norm square, 2 norm square was, what is z star norm z 2 norm, sorry 2 norm, we will omit this. Norm square is equal to summation mod z of n the whole square, the whole this square is here, sorry, z of n mod the whole square. So z star w in place of this z, we will get summation this here n belongs to, sorry, m belongs to z of m norm square ആണ് ഇവിടെ നമ്മൾ അതേ ഈ സമ്മേഷൻ ആണ് ഇവിടെ വന്നിരിക്കുന്നത്. സമ്മേഷൻ ദിസ് m belongs to z മോഡുലസ് ഓഫ്, ഇനി മോഡുലസ് ഓഫ് ഇവിടെ ഇസഡ് സ്റ്റാർ ഡബ്ല്യു ഓഫ് എം എന്ന് വരും ഈ കേസിൽ. അപ്പോൾ ഇസഡ് സ്റ്റാർ ഡബ്ല്യു ഓഫ് എം എന്താണ്? അത് നമ്മൾ നേരത്തെ തെളിയിച്ചു വെച്ചിട്ടുണ്ട്. ഇസഡ് സ്റ്റാർ ഡബ്ല്യു ഓഫ് എം എന്ന് പറയുന്നത് സമ്മേഷൻ എൻ ബിലോങ്സ് ടു ഇസഡ് ഇസഡ് ഓഫ് എം മൈനസ് എൻ, അതായത് കൺവല്യൂഷൻ ഇസഡ് സ്റ്റാർ ഡബ്ല്യു ഓഫ് എമ്മിന്റെ ഡെഫിനിഷൻ അത് ഡെഫൈൻ ചെയ്ത് വെച്ചിട്ടുണ്ട്. ഇങ്ങനെയാണ് അതിന്റെ ഡെഫിനിഷൻ. അതായത് ഇസഡ് സ്റ്റാർ ഡബ്ല്യു ഓഫ് എം ദ ഹോൾ സ്ക്വയർ ചെയ്യണം, അതാണ് ഈ സ്ക്വയർ ചെയ്തിരിക്കുന്നത്. വിൽ ബി ലെസ് ദാൻ ഓർ ഈക്വൽ ടു ദിസ്, ഇവിടെ ഈ പാർട്ട്, ഈ മോഡിനകത്ത് കിടക്കുന്ന പാർട്ട് ഇവിടെ കൊടുത്തിട്ടുണ്ട് ലെസ് ദാൻ ഓർ ഈക്വൽ ടു നോം ഡബ്ല്യു വൺ റൈസ് ടു 1/2 ഇൻറ്റു ദിസ് ടൈം, അതിവിടെ വരുന്നുണ്ട്. നോം ഡബ്ല്യു വൺ റൈസ് ടു 1/2 എടുക്കുന്നത് ഇവിടെ സ്ക്വയർ ആയതുകൊണ്ടാണ്. ഒരു മിനിറ്റ്, ഇവിടെ നമ്മൾ സ്ക്വയർ ചെയ്തിട്ടില്ല, രണ്ട് സൈഡിലും സ്ക്വയർ ചെയ്യുക. സ്ക്വയർ ചെയ്യുമ്പോൾ ഈ 1/2 അങ്ങ് പോവും, ഇവിടെ 1/2 പോവും. ബാക്കി ഇവിടെ കിട്ടുന്നത് നോം ഡബ്ല്യു വൺ അതിവിടെ എഴുതിയിട്ടുണ്ട്. ആൻഡ് ദിസ് സമ്മേഷൻ m belongs to z. Non w1 is a constant. We can take this constant in front of this summation. So this summation m belongs to z appears here. This modulus of this infinite sum will be less than or equal to summation of individual modes that we have earlier seen. So individual modes means mod z of m minus n the whole square into mod w of n. Yes, this comes here w of n the whole square means this raised to half ചെയ്യുമ്പോൾ ഹാഫ് സ്ക്വയർ ചെയ്യുമ്പോൾ ഹാഫും 2 കൂടെ കട്ട് ചെയ്ത് പോയിട്ട് 1 ആയിട്ട് മാറും, അവിടെ 1 ഉണ്ട്. ഓക്കെ, അപ്പോൾ നമുക്ക് ഇത് ഡയറക്റ്റ് ആയിട്ട് ഇവിടെ എഴുതാനായിട്ട് പറ്റും. വാട്ട് ഈസ് ദിസ് വൺ? ദിസ് ഇസ് ഈക്വൽ ടു നോം ഡബ്ല്യു വൺ അതുപോലെ എഴുതിയിട്ടുണ്ട്. സമ്മേഷൻ എൻ ബിലോങ്സ് ടു ഇസഡ് ഡബ്ല്യു മോഡ് ഡബ്ല്യു ഓഫ് എൻ ഇൻറ്റു സമ്മേഷൻ എം ബിലോങ്സ് ടു ഇസഡ് മോഡ് ഡബ്ല്യു ഓഫ് ഇസഡ് എം മൈനസ് എൻ. ഇതെന്ന് പറയുന്നത് ഒരു റിസൾട്ടാണ്. നിങ്ങൾ സമ്മേഷനൊക്കെ പഠിക്കുന്ന ഒരു തിയറമാണ്. അതിൻ്റെ പ്രൂഫ് ഒന്നും ഇവിടെ പഠിക്കേണ്ടതില്ല. ഇത് ഇന്റർചേഞ്ച് ഓഫ് ദി ഓർഡർ ഓഫ് സമ്മേഷൻ ഈസ് ജസ്റ്റിഫൈഡ് ബൈ എ തിയറം ഇൻ അനാലിസിസ്. അനാലിസിസിൽ ഒരു തിയറമാണ് ഇത് ഉപയോഗിക്കുന്നത്. ഓൾ ടൈംസ്, എല്ലാ ടൈംസും നോൺ നെഗറ്റീവ് ആയതുകൊണ്ട് നമുക്ക് ഇങ്ങനെ എഴുതാനായിട്ട് സാധിക്കും. ഇനി ഈ എം മൈനസ് വൺ സമ്മേഷൻ കെ ആയിട്ട് ചേഞ്ച് ചെയ്യുമ്പോൾ സമ്മേഷൻ എം ബിലോങ്സ് ടു ഇസഡ് മോഡ് ഇസഡ് ഓഫ് എം മൈനസ് എൻ ദ ഹോൾ സ്ക്വയർ എന്ന് പറയുന്നത് നോം ഇസഡ് സ്ക്വയർ ആയിട്ട് കിട്ടും. നേരത്തെ നമ്മൾ ചെയ്ത അത് തന്നെ. For any n substituting this gives norm z star w square. അതാണ് ഇവിടെ എഴുതിയിരിക്കുന്നത്. norm z star w square less than or equal to this one. This one become norm z1. This one also become norm w norm 1 w norm 1 into this one becomes norm z square. So norm 1 w here, norm 1 w here, both will get producted and we will get norm 1 w square into norm z square. That is, we have to prove that this norm 1 here we have taken this square here, so we will get norm z square will be less than or equal to the square by since both these items are non-negative, so we can take the root and we will get the 4.42 relation that is written here. Z star w, the norm square will be less than or equal to norm 1 w1 square into norm z square. The result we have to prove will be followed by taking the square root. Now this lemma is here, 4.35 lemma. 1 minute. Yes, we will prove that lemma. Lemma here, vw belongs to L1 of z and z belongs to L2 of z, then z star W cap of theta is equal to Z cap of theta, W cap of theta almost everywhere. And Z star W is commutative, and V star it is distributive also. These items we have seen in the finite case. Now we will extend it to L2 of Z, and VW belongs to L1 of Z. For proving the first part, we have this for Z belongs to L1 of Z. Now, first, initially we will prove for L1 of Z, and then we will extend it to Z L2 of Z. Now, for okay, we'll prove it now. Okay.